Lesson 33, activities. Find a function of the form f of t equals at plus b over t with a local minimum at the point 312. Okay, first let's use the fact that this graph is supposed to hit the point 312. What that means is that f of 3 is equal to 12, but I could also find f of 3 by plugging 3 into this, this specific form for f. So a times 3 plus b over 3. So that means that 12 is equal to 3a plus b over 3. I can't go any farther with that at this moment. Now I'm supposed to have a local minimum. Now I know minimums have to do with derivatives, so I think that means it's time to take a derivative of this function. Derivative of, remember, t is the variable, a and b are constants, so the derivative of at is a plus, now b over t, you could use the quotient rule, but this is really a constant over x whose derivative is negative the constant over x squared. It's that shortcut coming up again. So there's my derivative, and it says we're supposed to have a local minimum at the point 312. Now, if you have a local minimum, then your derivative at that point is probably 0. Your derivative could be undefined, but in most cases we've dealt with the derivative was 0, and so that means that our derivative is supposed to be 0. But actually, I have not taken advantage of the fact that I know that the t value at this particular spot is 3. And so it's not a matter of like solving this equation for t, it's that I know that this derivative is equal to 0 when t is 3. And so I get to put a 3 right there. So I guess maybe I could have written up here that f prime of 3 must have been either 0 or undefined, but 0 for most cases. And there you go. So that means we now have 2 equations and 2 unknowns. I'll clean this one up a tiny bit. A is equal to, 0 equals a minus b over 9. And so I've got the top green equation and then this last black equation, 2 unknowns, 2 variables. We can solve this. In this case, I'll use the method of substitution. In the previous problem, we subtracted the 2 equations, but we'll change it up a little bit here. Variety is the spice of life, even in calculus. So let's go ahead and actually I'll solve the other equation. We'll solve this equation for a. So that means that we can add b over 9 to both sides. And now that I've solved for a, I can substitute into the green equation. So 12 is equal to 3 times a plus b over 3. But then instead of a, we can put this b over 9 that we just solved for. So that's the substitution step. And finally, we get one equation with just one unknown in it. Okay, so 12 is equal to b over 3 is what you get when you reduce there, b over 3 there. 12 is equal to 2b over 3. Multiply both sides by 3 over 2. And we should get b is equal to 18. And once we know b, we can go back up to that purple equation at the top to find a. B over 9 was supposed to equal a, and so 18 over 9 is now equal to a, so a is 2. And so then we'll write our final answer here. Remember, f of t was equal to a times t, so that's now 2 times t, plus b over t, 18 over t. And that's the answer. But again, we're just going to spend, 2 minutes looking at this on GeoGebra. 2t plus 18 over t. So we're going to type that in right here. F of x equals 2x plus 18 over x. Where is it? Well, I don't know. I mean, like 18, so it's probably up above the screen. For example, if you plug in 1 for x's, you get 20 here. So I better go at least up to 20. So we'll drag. Oh, there it is. Okay, and there's probably another part in the third quadrant, I think. Yeah, there it is. But the only part we care about here is the point 312. So first of all, is the point 312 actually on the graph? Hey, it sure looks like it. And is the point 312 a local minimum? It sure looks like it there too. Let's actually confirm. We'll ask for the tangent line. So I'll click the point and I'll click the curve. And I want a horizontal tangent line to confirm that I've got a local min. And the equation of that line is y equals 12. And of course, that is horizontal. The slope there is 0. So everything worked out just fine on that one. That is the right answer. Okay, Pause if you haven't had a chance to read the text there, but we're going to jump into number 2, where we start labeling the graphs. A couple of ways to do this to know which one is which. So I guess the easiest way, if you just want to use your calculator, is to, for example, type in, I don't know, t equals 5, any number you want. I'll do 10. If plug in t equals 10 for each of these t's, then you should find y values, and that will tell you which one is which. So for example, I'll do this last one right here. So 6 times 10 plus e to the negative 0.2 times 10. And so what did I do wrong? Oh, it wasn't plus, it was times. Whoops. So I did second entry to recopy, and then I'll just delete. Okay, so when we plug in 10 for t into the last function, we get 8 and change. So does any of these have a y value of 8 and change? Yeah, it looks like it's this one right here. So if that one right there is the 6, and the only difference is the 6, 4, 2, then probably this is the 4 and this is the 2. But without the calculator, we can do this one because, again, the only difference is 2, 4, 6. And we know that multiplying the front of a function has the effect of vertically either stretching or compressing that function when you multiply the front of a function by a number. And so the biggest vertical stretch is going to be the one with the 6 on it, and then the 4, and then the 2 is the least vertically stretched one. So either way you slice it, we should know which one is which. So the top one is F3, and the middle is F2, and the bottom one is F1. Okay, what do you notice about the shapes? When you change the parameter a, so remember the only thing that was changing was the 2, 4, and 6, and that's the a right there. In particular, what happens to the t value at the maximum point and what happens to the y value at the maximum point as a varies? So looking at the maximum points on each of these 3 graphs, I'll go ahead and put dots. So we got 1, looks like it's around there, and 2, and 3, and we'll go ahead and label coordinates. So this looks like it's 5 and I don't know, like 3.8, something like that. And this one up here maybe is 5 and then about 7.4. And then up here is 5 and then it looks like it's around 11. Okay, so what appears to be happening to the t coordinates? Well, it looks like the t's are all the same. They're all 5. What's happening to the y values? Well, those ones are getting bigger as a gets bigger. So we can just write that. Max appears to occur at t equals 5 for any a. Positive constants a. The y values are getting bigger as a gets bigger. Okay, and then number 4, looking for the slope of a tangent line using calculus. So that means finding a derivative. So let's do that. F prime of t equals, okay, I see at, so what I'm thinking of as the first part of this function, and then e to the negative kt is the second part. Remember, t is the variable, a and k are constants. So what rule do we need to use to find a derivative? Well, we're going to use the product rule. First, in the red parentheses, at times the derivative of the second. E to the stuff becomes e to the stuff times the derivative of the stuff. The derivative of negative kt, t is the variable, k is a constant, is just the coefficient of t, which is negative k, plus second, copy e to the negative kt, times derivative of the first. Derivative of at is just the coefficient of t, which is a. So this derivative is fine. You can leave it right here for this problem, but I know we're going to do some more work with this derivative on the next page. So I'm going to go ahead and factor out the greatest common factor, just trying to help me in a future part of this problem. So greatest common factor, I see the plus sign in the middle separating my 2 terms. So what's the same in both of them? I see an a in both of them. I see an e to the negative kt in both of them, and that is all. So what remains in the front of that highlighted plus sign? After I factor out a and e to the negative kt, I see a t, and I see a negative k. I think that's it. And then after the plus sign, well, everything after the plus sign has been factored out, but you can't leave a blank there. You need a placeholder, and the placeholder, of course, is 1. And so our final version of my derivative here, f prime of t equals a e to the negative kt times, I'm going to bring that 1 first and then subtract k times t, just shuffling things around a little bit. Okay, so for this question, it wants us to find the slope of the tangent line at t equals 0, so that's going to be f prime of 0. And so we're just plugging 0 for all the t's. E to the 0 is 1. 1 minus 0 is 1. So at the end of the day, we should just get a. So the slope of the tangent line at t equals 0 is always a, whatever that number was in the front. So then it says use a straight edge to verify your result is reasonable. All right, let's come up here. Not going to do all 3, but let's do 1. So let's use a straight edge on the bottom graph at t equals 0. And you're going to draw a tangent line. And so a tangent line for me at t equals 0, maybe something like totally whiffed. How's that look? Maybe. Maybe. Okay, so if I'm looking for, I'm actually going to cheat because I think it's steeper than that. All right, so if I'm looking for the slope of that line, I'm going to use that point right there. That's the origin. And then I'm looking for another nice point that's on my tangent line, maybe this one right here. And so the slope of my line, slope of that one, is a rise of 3 and a run of 1. And so the slope there is 3. Is that the right answer? Well, the slope is supposed to be the number in the front of the, it's supposed to be a, it's supposed to be 2. Okay, so how come I'm off? Well, my tangent line wasn't perfect. It was a little bit too steep. So anyway, so that's what the calculation we just did at the bottom is saying. It's saying is that the slope for the bottom curve here at t equals 0 is 2, and the slope of the tangent line for the middle curve at the same t equals 0 is 4, and the slope of the steepest one at t equals 0 is 6. Always a. So that does seem reasonable. Okay, number 5. Now we're going to look at the effect of varying k. So let's label each of these. So the only change here is with a number in the parentheses. We got 1/5, 1/8, and 1/10. This one is probably tougher to analyze without the calculator, so we're just going to go right to the calculator. And I'm going to pick a number to plug in here for t. For example, t equals 20. These y values are very much spaced apart. So I'll just plug t equals 20 in to the last function here. 2 times 20 e to the negative 1/10 times 20. And so is the y value at any of these things right around 5.4? Yeah, it looks like that one. So I'm guessing that G3 is this one, and probably G2 is the middle, and G1 is the bottom. You could plug in more points into your calculator to know that that was right. So G3, G2, and G1. Number 6 says, for what values of t does it appear each one takes on its maximum? So let's put a dot at the max for each curve. So it looks like it's there, and then maybe here, and then right around here. On the previous question, all of the maxes were in a vertical line. They all happened to t equals 5. But here, the t is changing, in addition to the y coordinate changing. So for which values does it appear that each function takes on its maximum? So it looks like here, this is maybe t equals 5, and the next one is, looks like it's right around 8, and that last one looks like it's at 10. And lo and behold, 5, 8, and 10 are actually in the functions, right? 1/5, 1/8, and 1/10. So it looks like t equals 5 or 8 or 10. Okay, and now we're going to do some calculus with the function. The formula is given here. We want to find the coordinates of the local maximum. So finding the coordinates of a maximum of a function means take its derivative and make it undefined or make it 0. But we already took the derivative, so we're going to copy our simplified version of the derivative here in purple, a e to the negative kt times 1 minus kt. And once we have the derivative, we take it and we make it undefined, which it never is in this case, or we make it equal to 0, and that's the calculation we're going to do. And the reason we really like this factored form is that we could therefore set each of the factors equal to 0. So either ae to the negative kt is 0, or 1 minus kt is 0. Remember, t is the variable. E to the something is never equal to 0, so this one has no solutions. And the other equation will have a solution, again, solving for t. So we'll add kt to both sides and then divide by k. So we just found our critical point is that t equals 1 over whatever the k is. 1 over whatever, I guess the opposite of whatever number is sitting right there. Okay, but we're looking for the 2 coordinates of the max. We just found 1, so I guess what we need to do now is find f of 1 over k, taking the t value, the input value we just found, and plugging it into the original function, not the derivative, but the original function. We're looking for the y value here, the output. So the original function is right here. So we're just going to change those t's to 1 over k's. A times 1 over k, e to the negative k times 1 over k. So a over k, e to the negative 1. Now let's go ahead and put that e on the bottom. So a over k times e. So that right there is the y value. So that means that the coordinates of our point. Now I'm saying it's a max here. Technically, we should like verify by using the first derivative test that it is a max. We're not going to do that here. But assuming it's a max, the coordinates are input we said was 1 over k, and output is a over k e. Okay, number 8 says do some calculations with your result from 6 to see if the 3 functions graphed above confirm your result from 6 and a equals 2 for all 3 functions. Okay, so let's take a look. So looking at the 3 functions up above, I'll write the generic form of the function over here. So the generic form was g of t, I guess f of t, equals a t e to the negative k t. And so in our case, with these 3 functions pictured here, the a is 2 for each of them. So I'm just going to put a 2 there. And then the thing that changes is the k. And so what's the same in all of them is there's a t and a negative for all of them up there. And in our generic one, there's a t and a negative. And so the only thing, it's this negative and this t. And so the only thing that's different is the k. And so I guess the k must be the thing in the parentheses for each of these. So those are our k's. It's just the number in each parentheses. So let's just take a look at G1. For G1, k must equal 1/5. But in the work that we just did at the bottom of this page, we discovered that the maximum is at, we said it was 1 over k, comma, a over ke, which in this case, how much is 1 over k? Well, if k is 1/5, then it's 1 over 1/5, comma, and then a, we said was 2 for all of these functions, and then the k, again, is 1/5, and then there's an e. So what are we supposed to do with that? Well, let's clean it up a little bit. 1 over 1/5 is just 5. Hey, that's promising. And then this 1/5 on the bottom moves up, so it's really a 10 over e. And let's just go ahead and type that on the calculator to get a decimal. So 10 divided by e is right here above the division symbol. So that's around 3.7. It's roughly 5, 3.7. Does that look like the coordinates of our maximum for the bottom curve? Right here, 5, 3.7. Yeah. So the stuff that we did jives with this bottom curve. And in fact, because this 1/5 we saw, flipped over when we did 1 over k, right? You do 1 over that number right there. Then 5 made a lot of sense as the max. And for this one, if I flip over the 1/8, then I get 8, which makes a lot of sense for the t-coordinate of the max here. And I flip this one over to get the t-coordinate of the max there. So our work confirms what we see in the graph. Okay, so I think we're done with that one. Number 9, in an experiment, a group of male subjects rapidly consumed 2 drinks and their blood alcohol concentration was monitored over time. On average, their BAC peaked at about 43 thousandths of a percent 40 minutes after they took the drinks. Let C of T be their BAC, measured in thousandths of a percent, and T minutes after drinking, so the Y coordinate to the max is plain old 43. That's not 43 factorial, that's just 43. Okay, so use the results of 7 to find a possible formula. All right, so here's the idea. We are given in this particular scenario that the maximum occurred 40 minutes after these folks started drinking. So that's the T value. And their maximum concentration, the BAC, was 43 thousandths of a percent, which we're just writing as 43. But we did all that calculus work before on functions that look exactly like that to figure out that the maximum should occur at the T value of 1 over K and Y value of A over KE. So if, where is it here? So if we make these two things equal, that means that we can say that 40 is equal to 1 over K and 43 is equal to A over KE. So it's just making the coordinates equal individually. So that means therefore, so if I solve the first equation for K, I get K is equal to 40. You can either flip over both sides or cross multiply and then divide by 40. Did I say that right? Nope. I did say it right, but I didn't write the right answer. So K is 1/40th by flipping over both sides or cross multiplying and then dividing by 40. And then once I know that K is 1/40th, I can shove that into this other equation and solve for A. So that means that 43 is equal to A over, and then we just figured out K was 1/40th. And then I'll put my E right there, and I'm trying to solve this for, let's clean this up just a little bit. So the 40 is really upstairs next to the A. And then we're trying to solve this equation for A. So we're going to multiply both sides by the E, and then we're going to divide both sides by the 40. To get the value of A. And I think we can just type this on the calculator to get an approximation. Okay, so typing this on the calculator, 43E divided by 40, so 2.92. And so then again, I think the question said find a formula of this form, right? A possible C of T. So we'll write our final formula over here. So C of T, remember it was AT, so 2.92 T e to the negative KT, negative 1/40th T. And so what does that formula tell us? Well, it tells us the approximate blood alcohol concentration for these fellas T minutes after they started drinking. Right? And all we needed to know was, the maximum point, that it was 40 minutes in and that their blood alcohol content was roughly 43 thousandths. Okay, part B, over the first few minutes after drinking, the subject's blood alcohol content concentration increased at an average rate of about 3 thousandths of a percent per minute. Is this consistent with the results of part A, why or why not? Okay, let's analyze here. So over the first few minutes, that means roughly T is 0. And then it says that the blood alcohol concentration increased. So this is talking about a rate of change, C prime. C prime when? C prime roughly at 0. And it says at an average rate of about 3 thousandths of a percent. So what this is saying is that C prime of 0 is roughly 3. Well, is that true for the particular function that we came up with, right? Like we haven't calculated C prime of 0 yet for this thing. But actually, we did this in general early in this group of exercises. Way down here, we found that f prime of 0 is A, always the number in the front. A, remember, was this number right here. So f prime of 0 is automatically whatever is sitting in the front of this whole thing. So according to our work from earlier in this project, C prime of 0 for the function that we came up with is the 2.92, right? It's A. And so does the 0.003 of a percent make sense? Is it consistent with the results of the function we came up with? Yeah, we predicted 2.92. I mean, they're saying the right answer is 3. Our model is not that far off from the right answer. Should have been 3, and we got 2.92. So I'll just say that, that this is close to 3.